Hey everybody, Taylor Sparks back with another video. I got a question recently. Somebody asked me if I could help them visualize twins in calcite. So twins, let's start with what those are. So if you haven't seen my videos on twinning, I'll put a link in the notes below. But briefly, a twin is a type of boundary where you preserve mirror symmetry across it. For example, if you look at this diagram here, there's this green line at a sort of diagonal. And if you look at the crystal structure above that line and kind of below it, see this atom here? You could reflect it across that mirror to get this atom. This one could reflect to get that one, and so forth, right? Now, the two different crystalline regions, right, are clearly from the same structure, right? They have the same unit cell with the centering. Here it is, the same unit cell with the centering. But they're oriented in such a way that it is a type of grain boundary, but it's a grain boundary that preserves symmetry across it. That's a twin boundary. So in these crystals that exist, calcite, which is just calcium carbonate, twinning is pretty common. You can find them in nature, right? So if you see a crystal that looks like this, and it obviously looks kind of like a twin, right? That's an example of twinning. And you can find them in nature, right? So in this paper, here's a bunch of them. So it's showing you crystals, like you can see this twinning happening. And basically, it's very similar energetics when you get these sort of boundaries like that. So it's just as likely to grow on one as on the other. And so you end up growing on both, essentially. So in this paper, they're pretty awesome. They point out that there are 4 planes which are typical for forming twinning in the calcite crystal. And they've got them shown in this graph here. So figure 1 says, hypothetical calcite crystal showing the 4 forms that correspond to the possible twin planes. So you've got this pink face, the purple face, the green face, and the blue face. And these are labeled, right? Your 104, your 001, your 018, and your 012. So the first thing we're going to do in VESTA is just see if we can visualize those planes. Now, they don't have this white planes labeled, so I had to guess what those are. I took a guess at 111, and it gets us pretty close. Okay, so here we are. Here's what I've done here to create this structure. First, I had to get the calcite sieve card. You can do that just by typing calcite sieve. There's this awesome, at arizona.edu, they've got this awesome mineralogical database of sieve structures for minerals. And sure enough, this first one's the one I grabbed. It's pretty close to the other ones. So we grabbed that sieve card and we're going to open that in VESTA. When you open it, you don't get this big faceted crystal here. You have to create that yourself. You get it by going up to Edit, Edit Data, and then down to Crystal Shape. And here in crystal shape, this is where I add those facets, right? Where it said like the 104, the 018, the 001, the 012. I've just added those. Now, it doesn't look exactly the same as the one in the paper, right? Theirs is a little taller. That's because you can specify what the D spacing is. Like, okay, it's going to show you that plane and going to create a facet on it. But how far from the origin is that? That's a tunable parameter, and they don't have theirs labeled here. So I had to try out a couple values. I made this first plane, the 104, for example, 3 D spacings away from the origin. I made this one 5 D spacings. I made this one half a D spacing, this one 3. And if you change those a little bit, it will change the shape of this crystal a little bit. For example, let's take this green one, make it a little bit further out. That's going to shrink it. So let's take it from being 0.5 up to say like 0.75. It might be too far even. Let's try that. Yeah, it's actually so far that you can't see it anymore. Let's try 0.55. Yeah, now you see the green and it's just a little bit smaller, right? So to make it look exactly like theirs, you'd have to explore with the different D spacings, but more or less we get it. Now their white faces, we may not have the right face, again, because it's not labeled. I chose the 111 because it sort of gives us something pretty close to it. But it's possible that I didn't pick the right one there. I tried the 100 and the 110 and a few others, and this was the closest one I could get. So that's what we went with on this one. Okay. So we're able to visualize these facets where we typically see twinning. So the next thing in this paper is let's try and visualize a twin. They've got some great examples in here. Let's just pick the easiest one, which is twinning along the 001, the bottom of the hexagonal, the basal plane, right? And they've got this great example shown in figure 17. So it says here, figure 17, the calcite with hexagonal, bipyramid, and rhombohedron, showing the subtle distinction between an untwinned crystal and a twin, right? So on this left, this one right here on the far left, that is the scalenohedron, which is 324 facets with rhombohedron faceting. That's 104. So the rhombohedron is shown in green. These white ones would be the scalenohedron. So let's create that one. So I'm able to create that again by just loading the sieve card in. And again, I'm coming up here to edit data, coming down to crystal shape. And just like before, I'm adding the scalenohedron facets, that's 3, 2, 4. And again, I'm picking 5 despacings from the origin for those. And then I'm adding the rhombohedron facets, that's the 104. I'm doing those at 3 despacings away, and it's able to create the image that matches it. So in their notes, it says, note the zigzag edges around the equator of the crystal, right? These sort of zigzags. Well, we can see those, right? As I look directly on this along the B-axis direction, you can see those zigzags. So we're able to create that. Let's look at the next one. The center one, it says center. This is a hexagonal bipyramid, so a slightly different crystal habit, right? This is now faceting on 2, 2, 3, and then also shows the rhombohedron. So let's do that one. Here we go. So I've done the same thing as before. Edit data, crystal shape, 2, 2, 3. I did that one at a distance of 3 angstroms. This one also at 2.5 away, and we're able to get that structure. Now notice how it looks different. It looks very similar to the one before, right? Quite similar. So here's the left one. So these top and bottom rhombohedron facets are sort of opposite from one another. And this in center, they're doing the same thing, except we have this flat equatorial line, right? Slightly different. Now, if this was a twin structure, how would it look different? If it was twinned, it would preserve mirror symmetry, meaning this green rhombohedral facet would be oriented the exact same way on the other side of that twin boundary. But it's not here. It's clearly not. It's shifted, right? And so they show that here. In this last image says, okay, the right hand is the same crystal, but now with twinning on the 001 plane. Note the positions of the faces of the rhombohedron green, right? So this green is mirror symmetry to that green. So let's try and create that one. Okay, this one's trickier. It is harder to do. Here's how we went about doing it. We had to come up here, edit data. First we have to go to phases. In a twin structure, we're going to add a second phase, and we're going to orient it differently than the original phase. In fact, we're going to orient in a way that tries to preserve the mirror symmetry. So I've got 2 phases here. If you look at phase 1 and phase 2, they're both calcium carbonate, right? But we're going to now orient the second phase, right? When it comes down here, we're going to do it align orientation of this layer with respect to layer 1. If this layer is -1, -1, 1, -1, -1, 1, then we're going to orient it with all -1s for our layer 1. Second, up here in unit cell, we're going to come to our second phase. That's this one, it's called phase 2. And we're going to do a transformation because we have to have the axes change from right-handed to left-handed. Here is the transformation matrix. To go from that scenario, it's going to be 100, 010, 00, -1. We're going to make that change. And when you do it, it says heads up, this will change the handedness of the operation to left-handed. And you say, yep, no problem. When you do that, the catch is that for both of those phases, I had to show the crystal structure. So again, I would come back to edit, crystal shape, and I have both of them here. Again, for phase 1, I can click this to do it for phase 2. I've got the exact same habit, 223 and 104. Same thing here. And so they're superimposed on each other. But you can see that they are correct, that you have this triangle of green facing up from the first one is superimposed with this one. So this does actually allow us to show twins. Now I'm showing it with just the crystal shape. Of course, you could show it with the atoms itself, right? You could turn off the crystal shape and just do it with the atoms to show the twinning boundary. But that was an example of how you can do that. So you can do the same thing with the other ones in this paper. They're harder. It's more complex transformation. It's an easy transformation to just go across the z-axis. But that's the principle behind this, and something I didn't realize that VESTA could do. So try it out yourself. Let me know if you get stuck and what you want to see next.